Okay, hi everyone. So today, to begin, we're going to have a very short guest lecture by Lloyd. Lloyd is a PhD student here at CCRMA, and he's going to talk about accessibility for musical instrument design in general. So this is the first short lecture he's going to give, but there's going to be a bunch of other short guest lectures, so this should be like, what, 10 minutes or 5 or 5? Okay, 5 to 10. So, here we go.
Thanks, Ramon. Howdy, everyone. Like Ramon said, I'm Lloyd, use he, him pronouns. I'm a third-year PhD student here at CCRMA, and I bill myself as an applied disability studies scholar. So today will be part 1 of 3 of these sort of mini guest lectures. And today we'll be talking about a little bit of disability theory and discussing sort of what disability is. Then the next time I see you all, we'll go over the 3-ish sort of styles and schools of thought of accessible design. And then finally, in the last time I'll visit you all, we'll chat about applications to instrument and sound making. Cool. And if you have any questions sort of along the way, please feel free just to let me know, raise a hand, pipe in, whatever. So yeah, we'll chat a little bit about what is disability. So we're going to take just about 10 seconds or so. You can just think in your mind sort of concepts, people, words, anything that come to mind when you hear the word disability. Okay, and we'll maybe bring it back in. So some common responses, and sorry, just for the sake of time, we're not gonna pair and share. Some things that often come up when we do this sort of groupthink is disability as a diagnosis, something that has a medical label attached to it, or a societally legal, the term legally blind, legally deaf, or diagnoses like cerebral palsy. We can often think of people, communities, groups of people, like wheelchair users or deaf folks, sort of like large blocks of folks. We can think of the infrastructure designed to specifically support certain communities, elevators, ramps, braille text on signs. Maybe we can think in terms of systems of advocacy, legal representation, student unions and groups on campus. We might think of assistive technologies. These are technologies on the level of the person, such as white canes, using closed captions, things like that. And lastly, we can think of contexts, maybe that sort of highlight disability. For example, like noisy rooms or situations where the accommodations aren't provided, like old buildings without ramps or elevators, that sort of thing. Yeah, and so there are all these nebulous things that we might have floating around when thinking about disability. But what is disability exactly? Well, like any other human thing, it's really complicated. So there are a couple different, what we call in disability studies, models of disability. And I'll go over sort of the 2 big ones just to help us think through this. So the first one is what we would call the medical model of disability. So this is the sort of oldest Western model of disability. So the medical model views disability as an abnormality in the person, at the person level. Generally, it's viewed as a problem to be cured, and it's a meaningful deviation from the norm. So say, for example, sort of benign characteristic, like say having green eyes, might be a deviation from a norm, but not necessarily a meaningful deviation in the medical model. So the medical model also views this meaningful deviation as something where treatment is needed to correct it back to being normal. Whereas we have the social model, which developed in the 50s and 60s, and I'll be quoting scholar Nim Ralph on this one. So the social model views disability as being societally constructed. So a person is disabled by society's actions, by placing barriers of different types in all facets of life. And so this can be used socially through the built environment and through just institutional sort of daily norms. So in the medical model, we would use terms like disabled versus abled, and generally at the site of the body when referring to a single person. Whereas in the social model, we would talk about disabled versus enabled at the level of the situation. So a situation is disabling, or a paradigm of setup is disabling. So yeah, in the social model, a person is disabled by society or their context. And it is fluid. A person can be disabled in one situation and then enabled in another. It's not a fault, problem, or abnormality at the person level, and it's up to society to make these changes to meaningfully include and unlearn sort of our hierarchies of, who gets to be productive and how we value certain people, certain bodies over others. So it sounds kind of clear, maybe to certain folks. They're like, oh, like it's, wow, the medical model is maybe this like old school thing, and the social model is this new school thing. But they just describe different parts of the lived experience. So the medical model obviously is super helpful for folks seeking treatment, seeking sort of formalized support. And the social model is, again, potentially helpful for designing these sort of social interactions. And yeah, so the field that all of this comes from is disability studies. This is like, page 1 of the textbook. There's some great disability studies classes on campus, and there's also a new disability studies minor for undergrads offered through the School of Education. If you're interested in any of that stuff, please come chat to me. And the last thing before we go into questions is just some quick language. So first, the word and term disability is not a dirty word. Please feel free to use it. It's not a charity word. Just use it, as you would any other description of a person with care, but it's not a dirty word or a charity word. And just some things to orient us. One way we might sort of differentiate disability and be more specific is to talk about time in relation to disability. So in sort of the longer term, where disability happens more often in that person's life, we might talk about things like congenital or permanent disabilities. So this is something the person might have lived with for a very long time or all their life. Then we would have an acquired disability. So this is something that maybe comes later in a person's life, or like a situation kind of made a drastic change in a person's life. We would then have something that we might call a temporary disability. So this is something that kind of has a permanent end date. Very interesting thing, legally, pregnancy is a temporary disability in our legal model, which is interesting. And then lastly, we have situational impairments. So these are things that are very momentary, say for example, like pushing a stroller or things like that, momentary disorientation, all those sorts of things. And the last other axis I'll leave us with is 2 important groups of disabilities. One is what we might call visible. So this isn't being blind or low vision. This refers to how easy it is to read that someone has a disability, sort of socially. So for example, if they're a wheelchair user, if they use a guide dog or a white cane, if they primarily use sign language, these are very external, visible indicators of disability. And so societally, we might quickly associate the term disabled with those people. But there are lots of invisible disabilities. So things like chronic pain, dyslexia, mental health, cognitive disabilities, a whole rich suite, which I think we're societally, starting to become more accustomed to. And the tension between visible and invisible disabilities is something we're still very much grappling with, both in disability studies and on the campus, sort of institutionally and policy. But yeah, so there's a nice handy guide if you're ever writing about disability, but I won't go over that. You can definitely come talk to me. But a quick thing, if you're ever writing about disability, is you would use person-first language. So for example, if you're chatting about someone, you say like, oh, I made this thing, I worked with this person in Portsmouth, who is a person with acquired blindness, rather than like a blind person, unless that person uses that language to describe themselves. A nice neutral is person first. Yeah, and then I think for the sake of time, we'll pick up the next part when I come back. Any questions, thoughts, anything like that? I might then just jump to a reflection question, which is, how might disability intersect with the work you plan to do in this class? And obviously feel free to chat out loud if you want to take a moment to sort of reflect, that's cool. Yeah, sorry, no, that was a lot of information pretty quick. Yes?
Can I ask the same question from you? Like, how do you think disability can intersect with our project?
Yeah, thank you. It's almost like I planted you. So there's this great phrase in graphic design that you can't not communicate. So in the same way that like a visual thing is always going to, for those who perceive visually, is always going to say something. The most neutral thing you can imagine still says something. And so in the same way, whether we overtly choose to, interact with disability as something we consider in the design, disability is still a factor in our design, So folks with disabilities might come across the thing, our bodies are constantly changing. We might acquire disability while working with it. A common one that, is going around nowadays, COVID, long COVID, brain fog, all of these things that, we definitely know happen to maybe us, maybe friends, maybe family. So thinking about disability not as this like siloed thing that I need to be a specialist to go and do, but as this thing that's always there and is always present. It's just how much we choose to interact with and, overtly sort of deal with it. But yeah, so thanks for that question. Any other last questions? Before I run away and leave you. Cool, well, awesome. But yeah, so I'll be visiting 2 more times, and it's Lloyd May at Stanford.edu. Feel free to shoot me an email, also around the building on the 3rd floor if you have got any questions. Thanks so much for having me.
Well, thank you, Lloyd. So I just want to say that for your final projects in this class, potentially that's something that you might want to consider, right? It's been really a trend in the field of knives in the past couple of years, to do more work on accessibility of musical instruments and musical interfaces and stuff like this. So I would, recommend thinking about this, and see how potentially maybe you can orient your project in this direction. I'm not saying that you have to. I'm just saying that it's an option. That's yeah. Anyway. Well, thank you, Lloyd.
Awesome. Thank you.
Is it on?
I think so. And I turned you back up on the mixer. Is the
Oh, okay. I'm not sure if it was on. Maybe the battery is dead. Okay.
Well, sorry about that.
Hopefully people online heard. Yeah, see, it's dead.
Oh man. Well, so unlike people could shoot me an email.
Well, there we go. Okay, so how do I push this? So actually, what I just did is a very, very good example of the weird thing that happens in music technology that people never really think about it. It's like, this is a remote microphone, right? It's like a wireless microphone, and for some reason, it doesn't have a rechargeable battery. It has regular batteries, okay? So do you know why? There is actually a reason for that. Have you ever, and it's not just this one, it's most wireless microphones, they don't have a lithium rechargeable battery in them. So it might seem weird, but it's very much related to what we do in this class. So can someone guess why? From a purely design standpoint, they decided not to put lithium batteries in this.
It would be a lot easier to just replace batteries and recharge it in the middle of a show.
There we go. It's that they tried, but every time they tried, people would not buy it. Because sound engineers, during concerts, if for some reason your microphone is running out of battery, you don't have time to charge the battery, and so what you want to do is to be able to just put new batteries in the microphone so that it works immediately, So if you go to big concerts, halls or whatever, one of the main thing they have is piles of batteries, because it's easier to deal with that. It's obviously not very good for the environment. But Anyway, I think that's an interesting case of weird design implications just based on something very technical. Anyway, so today we're gonna keep talking about Faust. So we're mostly gonna do programming on our computers, just so that you get a global idea of what's gonna happen this week. Oh, and by the way, this is the first time this happens to me in this class. You know, like normally there's always a lot of people on the first day. Then the second day there's less people, and then the third day there's even less people. You know, and for some weird reason this year it's like every day there is more people. So it's kind of interesting. You know, like I guess that's because people can watch the lectures later on Zoom or whatever. You know, like but yeah, this is I guess people wanted to have a longer spring break this year, right? Okay, so this is what's going to happen this week. So today we're going to talk more about Faust, and on Wednesday we're going to start trying to export some of the things that we're doing in our web browsers for sound synthesis and audio processing on microcontrollers. Okay, so it means that we're going to give you the kits, not today, I lied, notice that I lied a lot, so we're going to give you the kits on Wednesday, okay? It's because we had to make some adjustments, you know, and it was kind of more convenient for us to do it this way. So on Wednesday we're going to give you the kits, we're going to look at the content of the kits, and we're going to teach you how to basically program the microcontrollers that are parts of the kits with Faust. Okay, so back to Faust. Okay, so at this point, I think you all know this thing. That's the Faust web ID. So one thing that I didn't talk too much last week is the different resources that are available to learn Faust and to know more things about what we're doing in this class. So the main resource for Faust documentation is the Faust website. It's the Faust Documentation website, so it's faustdoc.gram.fr. There is a link on the course website. So here, this is the documentation of the language itself, okay? So if you want to, it's kind of boring to read, you know, like that's not really something that you want to read linearly because it doesn't really make any sense. This website basically documents every single primitives and functions and syntax of the Faust language. So again, this is not something that you want to just like read linearly, you know, because it would not be very useful, I think. So there is a bunch of tutorials, and one of them, we're actually going to do it for Lab 2, and it's DSP on the TeamZ with Faust. The TeamZ is the microcontroller we're going to use for this class, and so part of Lab 2, part of the work you're going to have to do in Lab 2 is actually read this tutorial. So that's the documentation of the Faust language. See, there's like the manual, so if you want to know more about using the Faust compiler, you just click on this. Okay, so you can have a look at it. So then there is another resource which is quite important. That's the documentation of the Faust libraries. So this is faustlibraries.gram.fr. So the Faust libraries are the signal processing libraries that are built in Faust. And so when you go in the Faust web ID and you import stdfaust.lib, you basically import all the Faust libraries in the program that you're writing. And so you have the documentations of all the functions that are standard functions in Faust, okay? So for example, last week we used a couple of filters. So if you click here on filters, see there's a lot of filters in Faust, but the one that we used is Reson LP. So if you click on Reson LP, which is the resonant low pass filter, then you get the documentation for the resonant low-pass filter, okay? So you see there is a distinction between the documentation for the signal processing libraries and the documentation for the language itself, you know, like, because they are two separate things, okay? And again, you know, like, I know that some of you here never really did sound synthesis or audio processing in general. Some of you did a lot of that. So that's why we're kind of going very quickly on those things, you know, and so don't worry, you know, like, I mean, for your final project, if you don't know how to do like audio DSP too much, it's not going to be a problem, you know, we're going to help you with that, you know, like, I mean, every year, like, people focus more on the hardware aspect of the project or on the signal processing aspect of their project, you know, like, so what I'm saying is that there are different directions that you can take for your final project, and it's not really a big deal, you know, if you don't know that kind of things too well, you know, like, because obviously, again, there are some people in the class who are CCRMA students and who have like definitely little advantage on the signal processing front compared to other people who are taking the class, okay? So another good resource is the Faust Condenser course, so Condenser is a platform for online classes, but oriented towards multimedia, entertainment, and you know, that kind of things. And they have a lot of very cool classes. For example, there is one by Matt Wright, who's the technical director of CCRMA, and it's on Max MSP, you know, like, so usually most of the online CCRMA classes are available on Condenser, and it's free to watch the videos. You don't have to enroll and pay or whatever, you know, like, you know, this is just like so that you can check the videos, okay? So I think that's a pretty good resource if you don't feel too comfortable with Faust. So another thing that potentially at some point we can do, that's kind of going to depend on how many people who take the class are people who don't have too much background in signal processing. Maybe one day or for half a day, like, we could do like a workshop or something like this, you know, like, for starting from the ground up, okay? Because clearly I know there are always like differences, you know, like, so we can do this later during the quarter, you know, and because you're not really going to need that too much for now, but potentially for your final projects, this is maybe something that could be of interest for you, you know, like, so depending on interest and what people want, this is potentially something that we could schedule for, I don't know, like the middle of the quarter or something like this. And if I forget, maybe just remind me. Oh, by the way, guys, this is Kimia.
I'm your TA.
So Kimia is the TA for this class, and Kimia was she was doing a performance last week in Chicago, along with actually other people who are taking the class, like Sean, for example, right? So. Anyway, so if you need help, Kimia is the right person to ask. Great, so this is going to be kind of a messy lecture today, because I'm going to show you a lot of very different things, and the point is more for you to be like, oh, how do I do this in Faust, you know, and I already know, like, Chuck or whatever, you know, or C++ or any language that you might have used to do audio processing. And so the point of today is just like to show you like different programming techniques that might differ a little bit from the one that you're used to with other platforms and environments. So, okay. So one thing that I want to say first is that Faust is completely open source. Okay, so it means that if you look for Faust on GitHub, you're going to find the source code of Faust. So you see that there is two different Faust. There is one that does stream processing in Python, and then there's the second one, which is one that you want to use. Okay. So, well, there are two different things. So that's also a documentation on its own. You know, like so if you want to know more about Faust, one way to know more about Faust is actually to look at the source code of Faust. You know, and so. It is a community-driven project, so even though like the core developers for the compiler are mostly based at CCRMA and at the place where I work in France, there is also a lot of people everywhere in the world who actually contribute to this programming language. And so there is a repository for Faust, but there is also a repository for the Faust libraries, and that's what I wanted to show you. Okay, so here on GitHub in Faust Libraries, you have the source code of all the Faust libraries. So whenever you call a function in Faust, like resin LP last week, you're going to find the implementation of the function in the Faust Libraries repository. So this is very convenient, you know, because if you want to learn how those things work, you can always look at the source code. Okay. So the reason why I'm showing you this now is because very often you're potentially going to want to hack some of the functions that are implemented in the Faust libraries. And I just wanted to kind of show you an example of that. So in the Faust libraries, you have very high-level functions, meaning that some functions already have a user interface built in. Okay, so that's something that you can do with Faust. You can create a function, and you can actually put a graphical user interface directly in that function. And usually these functions are available in a library which is called the demos library. And so you know that in Faust, the first thing that you put when you call a function is the prefix that gives you access to a specific library. So when I say DM, I'm like, okay, I'm accessing the demos library. And so if you look at the source code, here it is. So demos.lib. And this is all documented, right? Like if you wonder like what the prefix for the filter library is, then just look at the documentation. You know, like this is easy to guess usually. You know, like but maybe not something that you can guess automatically. Okay, so so you see that if I say dm dot, then I get a list of all the functions that are available in the demos library. But actually, I'm gonna try with PM. PM is the physical modeling library, and so in the physical modeling library, there's a clarinet UI model. Okay, so you know that if you want the Faust online ID to compile in real time, just check this box. Okay, and so you see that this is a valid Faust program. Like the Faust compiler is happy. And this function here just implements a clarinet physical model. It's ready to use, and because it says UI, it means that it already has a user interface in it. Okay? So if I run this program, here is what I get. So I get a, oops, sorry. So I get a user interface, and you can see that I can control pressure. Okay, so see that this is a clarinet physical model. So here I'm just controlling the amount of pressure that I'm putting in the tube of the clarinet. And you can also see that because this is a physical model, there is a bunch of physical parameters that I can control. So I can control the length of the tube of the clarinet, I can control the reed stiffness, I can control the bell opening. The bell is like the end of the clarinet. And so so if I change the length of the tube, what's going to happen? Yeah, it's going to change the pitch, right? So cool. So all that to say that there are some functions in Faust that already have a user interface built in. Okay, so This is convenient, but it's also potentially confusing, and especially in your specific case in this class, where you guys are actually gonna make your own physical interfaces to potentially control something like this, right? So I don't know if you saw when I was typing, but there's also Clarinet UI MIDI. So what is the difference between Clarinet MIDI and Clarinet UI MIDI? So you can see that Clarinet UI MIDI has a very different interface, and that interface has a button. Okay. So it means that this interface is designed to be mapped to a piano keyboard. Okay, and this is why it says MIDI. Okay, so can you tell me or maybe guess like why this can be mapped to like a MIDI keyboard, and why this cannot be mapped to a MIDI keyboard? Like, do you get like the difference or? Yeah.
Because in this case, the pressure is a sliding scale, but in the case of the MIDI, you're either pressing down the button or you're not pressing down the button.
Exactly, yeah. So basically, with this example here, the way you're gonna control the main parameters of your instrument is by controlling the amount of pressure, of physical pressure you're putting in the model of the clarinet. And if you want to change the pitch, you have to change the length of the tube, okay? So those two parameters are somewhat incompatible with a MIDI keyboard, right? Like if you wanted to map this to the piano keyboard that we have here, you can't really just do this out of the box, you know, like, because there is no button to say on or off, okay? There is no way to be like, oh yeah, this is like, this pitch on, like this note corresponds to this tube length or whatever, you know, like, so we're missing some elements here to make this potentially compatible with a MIDI keyboard. So the reason why I'm talking about this is because when you start thinking about the interface you're going to implement for the different things that you're going to write in Faust, the parameters that you make available, they have an impact on how you approach the interface, right? So potentially this would work, like this specific example here would work very well if with your Teensy you were to have, say, like a breath controller. You know, like if you were to get a sensor to measure like a blow sensor, you know, like a sensor that you can blow on, you know, and then potentially you could map that to pressure, right? Same thing for tube length. Maybe the tube length of your clarinet could be mapped to a physical slider, you know, and so in that case, the interface that you're building is not an interface which is meant to be based on a keyboard, okay? But it is an interface, you know? And in fact, I strongly encourage you to think about that kind of stuff when you're gonna work on your final project, because very often, if you control physical parameters of a synthesizers with continuous values, as opposed to discrete values, right? Like the piano is a very discrete interface. Often your instrument is going to sound much, much more natural because you're going to have more control on how the sound is produced. You know, like you remember in the first class, we talked about the clarinet versus the piano, and the fact that with the clarinet, you have more control on the sound that is being produced than with the piano, where everything is very discrete. So, depending on the kind of interface you're going to build, this is something that you want to like keep in mind, you know, and really take into consideration. So basically, the main difference between Clarinet UI and Clarinet UI MIDI is that for Clarinet UI MIDI, there is an extra layer on top of Clarinet UI that basically does something that when you press the gate button, it's going to control the pressure of the clarinet using some kind of envelope generator, okay? Because that's what happens in practice. Like if you're playing a note like pressure doesn't increases like immediately. Like it takes some time before you reach a certain level. You know, like so the envelope of that is mapped to pressure is probably going up. You know, and then it's going to be steady for some time, and then it's going to progressively going to go down. So here, that's what the gate button is doing. Like if you press the gate button, you're basically controlling the envelope of the pressure parameter of this physical model. Does that make sense, or like? So this is not really Faust per se. You know, like it's more like general things about how you map physical controllers to sound synthesizers. You know, like but this is already something that we have to deal with here. So so that's why I kind of wanted to talk to you about it like very briefly. Okay, so clarinet UI MIDI is declared in physical models.lib. So if you go in the source code of this library, so this is GitHub, and on GitHub, if I go in phys models, and in phys models, if I look for, no, I don't want to print, if I look for clarinet underscore UI. Okay, and then you see that here we have the definition for clarinet UI, and here we have the definition for clarinet UI MIDI. And so you see the definition for clarinet UI is just basically a blower UI, because you know, like you need a physical person to blow, or like program to blow in the model of the clarinet, just connected to the clarinet model UI. Okay, and so I suppose clarinet model UI is declared here, and you can see that clarinet model UI is basically based on clarinet model. Clarinet model is a function that takes, sorry, this is kind of small. Clarinet model is a function that takes couple of arguments. The first one is the tube length, the next one is the pressure, reed stiffness, and bell opening. And so basically what clarinet model UI is doing is just mapping those different parameters to user interface elements. Okay, so you see it's fairly legible, you know, like, and so the reason why I'm showing you this is because at some point in this class there's probably going to be a point where you're going to have to go in the Faust libraries and do something like this, you know, like where you're like, okay, I need to add a parameters, or I need to change the mapping of a parameter. For example, you think that the tube length parameter should not be a value between 0.01 and 3. Now you can just copy and paste that in your program, and you can make those modifications by hand. Well, in fact, let's do it. You know, like so here I'm just going to copy this function, and I'm going to paste it in my Faust program here. Okay. So currently I'm calling pm.clarinetui MIDI, but I want to call the local version, so the version that is declared in this file here. So to do this, I'm going to get rid of PM, and I don't want to call the MIDI version, I want to call the UI version. Okay, cool. So you see that if I put the PM here, the Faust compiler is happy because I'm accessing the function that is declared in the libraries. And if I get rid of PM, now I'm calling the function that is declared here. Does that make sense, or? Yeah. Okay, but you see that I get an error, yes, error is that, oh yeah, done something pretty dumb. So we'll do, I also need to copy and paste this one, you know, because this one has the blower. So I'm just gonna copy this here. Okay, so there are two functions here, right? There is the clarinet UI, which is a blower UI connected to the clarinet model UI. Okay. clarinet model UI is now declared here, okay? Blower UI is not declared in this code, but I'm gonna use the standard version of the library. So here I'm gonna put PM dot, okay? So now the compiler is happy with that, but there are still a couple of things that it doesn't find, okay? So clarinet model UI here is based on clarinet model. Clarinet model is defined in the physical modeling library. So here I need to add PM to this, okay? Now the compiler is happy, okay? Because here I'm using the version of clarinet model which is defined in the libraries, okay? But I made my own version of clarinet model UI which is defined in here. And so say that now I want the default value for tube length to be 0.5, then I can do it, okay? So the reason why I'm showing you this, is that what we really wanted to do in this class is not necessarily to completely understand the way Faust works, because it's pretty complicated and there's a lot of things to know, and it's not really the objective of this class. But instead, what we wanted to do is to be able to do stuff like this, where you're like, oh, I'm reusing this function that already exists, I'm gonna hack it to try to make something new, starting from something that's already out there, okay? Does that make sense, or? Yeah?
Can you repeat how you found the original function?
Sure. So, so basically, well, for all these models, like clarinet or flute or whatever, usually they're defined in the Faust physical modeling library. There's so they're mathematical physical models of musical instruments. So this is not based on samples of like recording of a clarinet playing or whatever. It is really like a clarinet synthesizer, basically, okay? So the way I found this is that I know that all these models are in the Faust physical modeling library, okay? So basically, if you want to get an exhaustive list of everything that's in the Faust physical modeling library, you just do PM dot, okay, and then you have the list of all the functions that are available in the Faust physical modeling library, okay, and you can see that there is a lot, but some of them are fairly like self-descriptive, and see that here there is a violin UI, so it means that if you have a clarinet UI, you probably also have a violin UI, or you have a trumpet UI, or you have a flute UI, and so the first thing that you want to do is to potentially call these functions. Okay, so here I'm calling the violin, and then it's already working here in the web ID. Okay, so here I can change the bow velocity to produce sound, and then if I want to hack this, all I have to do is just to go in the source code of the Faust libraries, which is on GitHub, right? So on GitHub, if you go to look for Faust libraries, you're gonna find this page, and on this page, you're gonna have the source of every library which is available in Faust, okay? And so what I did here is that I just went in physmodels.lib, and then I just did a search in the page for clarinet UI, and then I found clarinet UI. Okay, so as part of the first assignment for this week, this is something that you should try to do, like assignment 0 is not graded, it's open, but the whole idea of assignment 0 is to sort of get a basic understanding of how those things actually work. So, is that clear, or? So I'm just warning you a little bit, like today, especially like the second half of the lecture today, is going to be a little bit harder to follow for those of you who don't have a background in audio DSP or stuff like this, but I'm doing it because there are some people here who do, and I feel like they also need to get that a little bit, So don't be afraid if the next stuff that we're going to do is a bit harder. It's not going to like impact the quality of the instrument you're going to make in the end, and just I think it's important to mention that. Is that my sometimes. Not really sure why, but okay. Cool. So if you don't have more questions on this, I'm not sure why it's doing this. Okay. If you don't have more questions on this, I'm just going to keep going and talk about something very different. Okay. So let's start over, and I'm going to just put process in here. Okay, so those are like what I want to show you here is something that is a little bit more related to the syntax of Faust and some stuff that can potentially be confusing with it. Okay, so say that, for example, you want to make a mixer. Okay, so a program which is going to take, for example, two audio signals and add them together. Okay. So I'm going to call this program mixer, okay? And if you were to implement this mixer using a more standard programming language, the way you would do this is probably using an imperative way of programming, where you would say, okay, mixer has one argument. This argument is the input, okay? So I'm calling it X. Okay. Usually in audio signal processing, because we're talking about differential equations, the input to your equation is X and the output is Y. Okay, so that's why here I'm calling my input signal X. Okay, so I'm going to say there is X1 and there is X2. Okay, because I want to mix two signals together, and then my mixer can be X1 plus X2. Okay. Then if I call mixer in here, this is what I get. You see that I get a function with two arguments, x1 and x2, and I'm adding x1 and x2 together, okay? So, the first thing that's potentially a bit hard to understand in Faust is that because it's a functional programming language, there is a lot of things that are implicit, okay? Here, I just call mixer. Where is the input? Where is the output? I don't see them, right? Well, you don't see them because they are implicit. So if you call a function just like this without specifying the arguments to this function, okay, they automatically become inputs and outputs to this function, okay? And so here, because I'm calling mixer on the process line, the only things that the Faust compiler can do in terms of providing inputs and outputs to this function is to provide physical audio inputs and physical audio outputs, okay? So if I call mixer on the process line, the output of mixer will automatically be connected to the physical output of the system, which here are the built-in speakers of my computer. And the inputs will automatically be connected to the default inputs of the system, which is specified here in the Faust Web IDE, and then that's, well, here an audio file, okay? But it could be a microphone or whatever you decide it to be, okay? So, yeah,
Is mixer a custom function?
I just made it. Yeah, like mixer is a function that I just made from scratch. You know, like mixer is just x1 plus x2. Okay. So, if I wanted to be a little bit more explicit, because again, here we're being very implicit, I could make it slightly more clear by saying that, okay, I have a program that has two inputs, okay, and those two inputs are connected to mixer, okay? So you know that in Faust, underscore stands for a pass-through. It's a signal, okay? It's the objectification of a signal. The comma is to put two signals in parallel. So here, I'm saying that I have a program that has two signals in parallel as the inputs, and those two signals in parallel are connected to mixer, okay? Same thing, if I wanted to be slightly more explicit, I could say that mixer has one signal as an output. What I'm doing here is completely useless. It's just to show you how it works, okay? So I don't need to do what I just did. I can just call mixer as is, you know, but then you can also do this, you know, like, but then it just makes your code heavier, okay? So, the reason why I'm telling you all these things, you know, is because if you look at the implementation of different functions in the Faust libraries, you're going to see this kind of syntax, you know, and so it's just so that you know, it kind of rings a bell in your head. If you look at the implementation of a specific function, you're like, oh yeah, I remember he said something about this, you know, like, yeah. All right, so you can actually be even more implicit, okay? So here we're being extremely explicit, okay, because we're really describing everything, you know, we're like, okay, we have mixer function with x1 and x2, we add them, you know, and then when I call mixer in process, I clearly states that there's two inputs and one output, okay? So then we can do the opposite. We can be very implicit, you know, so to be very implicit, well, of course we need to get rid of this, which doesn't change anything, okay? And then I'm gonna define a different version of mixer, and this version of mixer is just gonna say that mixer is equal to plus. So that's the same. Like from a mathematical standpoint, there is no difference between mixer equals plus and mixer x1, x2 equals x1 plus x2. Like those two things are exactly the same. Like once your program is compiled, it's not going to make any difference. Okay, so this is very implicit. Okay, so how can the Faust compiler know what's going on here? You know, like so basically, plus is seen as a function because it's a functional programming language, right? So plus is a function, and plus is a function that has two arguments and one returns one thing, okay? And so so automatically, because the compiler has this ability to abstract everything that you give to it, it's like, okay, so mixer is a function that has two arguments, and those two arguments are added together and return something, you know? So so that's why I don't need to specify the arguments here, because they are completely implicit. And the compiler can guess what to do with this, okay? Is that completely obscure, or yeah?
How does it know there are only two inputs?
Because if you do an addition, there's only two inputs, right? I mean, it's like if you add 1 plus 1, well, 1 and 1 are the two inputs to your plus function, right? Like plus is a mathematical function that takes two arguments, this one and this one. So like you can't, if you want to do an addition with 3 numbers, then you need another addition, right? So that's how it knows, you know, like, because that's the only option, basically. Like, if you do a plus, then the only thing that it can do is to add two numbers. Not 3, not 4, not 1. There is only 2, right? So, yeah.
How would you write it if you wanted to have like mixer going from 3 to 1? Could you do like 2 pluses? I feel like that would just make 4 to 2.
So then no, like then like it's too hard to like the compiler cannot guess what to do with that. You know, I can say like if you wanted like to do like this, then it doesn't really make any sense. You know, like because then it doesn't really know what to do with the different arguments of your function. So it only works if it's very clear and it's possible, you know, like, but there are many things that are impossible to write. So in that very specific case, no, it's only 2, you know, and usually for basic mathematical operations, there is only 2 inputs anyway, you know, like, okay. Now, just to sort of finish confusing you with this, there is, you can do something which is somewhere in between, and that's what we call partial application. It's a computer science term. So here I can say, I can specify one of the 2 arguments of my plus function to be a static argument. So for example, say that you want to create a function that adds 1 to something, then you can write something like this. Okay, so here what you say is that I have an add. This add has 1 argument which is already specified and it's 1. So it means that I only partially completed the operation for my addition, so only one of the arguments becomes implicit. Okay, and in that case, it's the other argument. Does that make sense? So you're never really going to want to write Faust code like this in 258, but because it's too abstract, maybe, or I don't know. If you want to, you can, you know, like, but it's just that at some point in all the different codes you're going to read, you're probably going to see things like this, you know, like, so the only reason why I'm showing you this now is so that you don't get too frustrated or confused when you're going to find code on the web or whatever that is doing stuff like that. Okay? Yeah.
What's the function of the parenthesis?
So that's a good question. The parentheses here are here to disambiguate the fact that 1 is an argument of the addition function. Because, for example, in some cases, you might want to do this, you know? It's like you're adding -1 to your function. If you don't have the parentheses, then you do this, and then it's very confusing for the compiler, you know, like, it doesn't do the right thing, you know, like, so the parentheses are here to disambiguate the fact that you want to do partial application on your function. That's a good question.
So it was, the parentheses is not necessary if you're just adding 1, or?
Well, if you do this, it doesn't really do what you want, you know, and so this is weird actually. This should not even like be valid. So that it doesn't mean the same thing basically. Like so, it's funny. Okay, I guess it decides that. Anyway, if you want to do partial application, you need the parentheses. Cool. Do you have any questions about this, or? Okay, now I'm going to show you something harder. And you're probably like, oh fuck, this was already pretty hard. So again, like this is not necessarily something that you're gonna want to use too much for 258, you know, like it's just so that you know it's there, you know, like, you know, and that's the whole point of what we're doing today. So currently, we only looked at implementing things that go from left to right, okay? Except that in audio DSP, very often you want to create feedback. So you want to have block diagrams that go from left to right, but potentially also from right to left, so that you can create a loop, okay? So how do you create feedback in Faust? Before we do it, I just want to show you a very, very basic example of a filter implemented in Faust from scratch. And that filter is just feed-forward filter. So for those of you who know what I'm talking about, it's like a 1-0 filter. Okay, so it's an FIR filter, not an IIR filter. Okay, so I'm gonna call this filter. Okay. And you know, the first thing that you want to do when you have a filter is to have a delay, right? How do we create delay in Faust? So if you want to create a one sample delay in Faust, you just use an apostrophe. Okay, so this is not a filter currently. This is just a one sample delay. So can someone tell me what's going to happen if I run this program? And if I send sound in it? If I can try. Okay, running the program. Okay. So what is it doing?
Is it just outputting the same thing but one
sample.
Yeah, one sample later.
Yeah. Okay, so why? Seems like it's not really doing anything, right? Why? How long is one sample delay? It's very short, you know, because I don't know what the sampling rate of the web browser is, but it's probably like 48 kilohertz or something like this, you know. So one sample at 48 kilohertz, that's very, very short. In fact, do you know how much it is in seconds? What's the operation? Say that the sampling rate here is 48 kilohertz. What would be the duration of my one sample delay in seconds? Yeah, it's just
the sampling rate is also it is 48,000.
What?
The sampling rate is 48,000.
Oh, okay, great, thank you. So if I do 1 over 48,000, then I get the length of this delay in seconds. It's very short. So it's so short that you don't hear it, okay? If you wanted to have a longer delay, then you could use the @ operator in Faust, where you can actually specify the number of samples that you want for your delay, okay? So here, for example, if I say 48,000, now I have a delay with the length of 48,000 samples. That's 1 second, okay? So now if I run the program, and if I send audio in it, 1 second, okay? Cool. So now say that, because that's what I wanted to do. I wanted to do a filter. I didn't want to do a delay, okay? So if I want to implement, say, a 1-0 filter in Faust, so just as a very, very quick reminder, a 1-0 filter looks like this. It takes an input and it has an output, and it basically delays the input by 1 sample, and then it adds it back to the original signal with some kind of coefficient, which we usually call B1, okay? So that's a 1-0 filter, okay? How do I implement this block diagram in Faust? Well, it's very straightforward. You say that you want an input signal, which is the underscore. Then you split this input signal into two different signals, 1 and 2, okay? One is going to be delayed by one sample and multiplied by B1, which is an argument of filter. And then you basically merge those two signals together. That's your 1-0 filter, okay? So take an input, I split it into two different signals. One is delayed by one sample and then multiplied by B1. The other signal, I just keep it the way it is and then I merge them together, okay? So that's a 1-0 filter in Faust. So, like, for those of you who know about that kind of stuff, you can see that Faust is very convenient for writing filters because with just one line of code and just a few characters, you can actually write a filter, which is not something that you can do easily with other programming languages. Okay, so I wanted to show you how we do feedback. So say that now I want to create an echo, okay? So what is an echo? An echo is an algorithm that takes an input, okay, so x of n, it has an output y of n, and then we have a delay here, and it's more than one sample, otherwise we're not going to hear it. And basically, now the signal is going backward, okay? So we have feedback, and here we have some kind of coefficient to control the amount of signal we are re-injecting in the loop, right? So an echo looks like this, right? So you know what an echo is, right? You know, like if you go hiking and you say echo, you know, like, and then it's gonna do echo, 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 echo. Okay, so here that's what we're trying to do. Here we're trying to make a model of that, okay? So a model of you saying echo and repeating that over and over again until there is no more sound by removing some energy in the signal every time, okay? So to do this, we need to create a feedback loop. And that feedback loop has a certain number of samples and it has a feedback coefficient that we call f, okay? So in other words, if we were to write the differential equation for this, we would have something that says y of n equals x of n plus y of n minus 1 multiplied by f. Okay, so that's the differential equation for our echo. Okay, so how do we do this in Faust? Okay, that's hard. So don't be, again, don't freak out. I know that, because I know that some of you are probably freaking out a little bit right now. You know, like, I'm gonna be so lost in this class. No. Like, this is gonna be okay. You know, like, this is the only time we're doing this. Okay, and later it's gonna be like not about this. You know, like, and so like everyone has something to bring in this class. You know, like, so don't be afraid if you're completely lost right now. Okay, that's normal. Okay, so I want to create an echo, and that echo is going to be using an operator in Faust, which is the tilde operator. Okay, so tilde in Faust is what allows you to create feedback in a block diagram. So I'm gonna say that we have A and B, okay? So tilde has two arguments, one on the left, one on the right, and those two arguments are A and B. Now what I'm gonna do is I'm gonna use this thing, which basically allows me to create local variables, okay? So this is where I'm going to define A and B. So here, I'm saying that A and B, which are going to be declared in here, are only visible within the scope of echo. That's what width is for. Okay. So I'm gonna say that A is equal to something and B is equal to something. Okay. And then I'm gonna call echo here. Okay, and then I get this kind of fucked up block diagram, which doesn't really mean anything. Okay, so what are A and B like in that context? So A stands for all the things that are going forward, and B, which is on the other side of the tilde, is everything that's going to go backward. Okay, so if we look at the block diagram that we want for our echo, so this is the forward portion of the diagram, this is the feedback portion of the diagram, okay? So basically, this is going to be A, and this is going to be B, okay? So what do we have in A? In the block diagram? Like, practically.
Audio signal?
What?
An audio signal?
Well, we have an input, and after the input, we have an addition, okay? So, that's what I'm gonna say here. I'm gonna say that A has an addition, okay? So now we have a block diagram that already makes slightly more sense. So this is A is an addition. The addition has two arguments, okay? One is actually getting the feedback, because the feedback is already implemented, and there is nothing in it, but it exists because of the underscore. And then the other argument of the addition, because it's not specified anywhere, becomes implicit. So in that case, it becomes an input to the system, okay? Cool, so we have the bottom portion of the block diagram. Now we need to implement the upper portion of the block diagram. Okay, so what do we have here? That's a delay, okay, and that's a multiplier, okay? So this is gonna go in B, and so I'm gonna say that I have a signal. The signal is gonna be delayed by a certain number of samples. So for now, I'm gonna put something random like 20,000, okay? And I have a multiplier, and the multiplier is F. And so I'm just gonna say that the result of this operation is going to be multiplied by F, okay? F is not defined for now, so I'm just gonna put it as an argument of echo, and I'm gonna say that F is 0.5, okay? So, does that sort of make sense, or is it like, yeah?
For that underscore asterisk part, could you do that like one, what did you call it before, the
Yeah.
static,
Yeah, like I can do like partial application for this. That works. Yeah, good point. And I can also do it for the at. So I can put parentheses here, and that works. And in fact, if I do this, because of the parentheses of partial application, I can actually get rid of this, and I can get rid of the parentheses here, and there we go. And so now it's even shorter. I was putting the underscores to not make it too confusing, you know, like, but like, now this is like a very like Faustian way of writing things. And it's the same as what we had before. Yeah.
Where the feedback starts on the diagram, where it leaves like A.
Yeah.
And it's like, yeah, like, is that just a graphical like thing to show you it like why it's two things leaving that become one thing?
That's a very good question. So tilde does two things. It creates the feedback, but it also preserves the signal to go forward, okay? So that's the two things that it's doing. And then the little thing here means that there is an implicit one sample delay.
Okay.
And so that's yet another hard thing to understand about Faust. So if you write a differential equation which is recursive, you can write something like y of n is equal to x of n plus y of n minus 1, right? Could you write this? No, you can't write this, right? Because, you're looking at a time series here, and if you write this, it means that you need to know the value of y of n before it's computed, right? So it means that like here you're trying to look ahead in the future, but you don't know what the future is, right? So you need the one sample delay here, and because you need the one sample delay to make this solvable, you have this little thing here that says that there is a one sample delay and it's implicit. Okay, so it means that this echo algorithm doesn't have a delay of 20,000 sample, it has a delay of 20,001 sample. So for an echo, it's not really a problem because there is not going to be a huge difference between a delay of 20,000 samples and a delay of 20,001 samples. But if you're implementing a filter, then it actually matters a lot. So you actually have to sort of keep that in mind. Okay, before I take more questions, I'm just going to play sound, so that we see what it's actually doing. So I'm going to plug this back. Okay, and okay, so playing the sound. That's the echo. Okay, so if I were to increase this value, like make the delay longer, then the echo is much longer, much slower. See, there is only sound going from one speaker. So if I want to have sound coming out of both speakers, you remember I need to do the splits and then this. Remember, we did that last week. Cool. So if I increase the feedback, then it's gonna go over and over again for longer because I'm removing less energy in the system. And if I make this shorter, then it's faster. Okay, so there's an echo function in the Faust libraries. You don't necessarily need to make your echo from scratch every time you want to have an echo. The main reason why I'm showing you this is just so that you know that those things are possible and that they are out there. It's just eventually you're probably going to run into some kind of code that shows you stuff like this. Do you have any questions? Cool. Okay, I'm going to show you another example of feedback in Faust. That example is the last example I'll show you today. That's the hardest one. Okay, so I'm sorry, but So I want to show you how potentially we could try to implement. I don't know why it's doing this. But, I want to show you how we could try to implement an oscillator from scratch. Okay, so you know, there is the easy way of doing things where if you want an oscillator, say like a sine wave oscillator, you just call os.osc and you give it a frequency, and that's your sine wave oscillator. Okay, so I'm going to show you potentially how using the tilde operator you can make a sine wave oscillator from scratch. Okay. Cool. So to do this, the first thing that we need to do is to implement a counter. Okay, so something which is going to count one by one. So when you work with Faust, you always have to resonate in terms of block diagrams. Okay, so what is the block diagram of a counter, which is going to count one by one? So it's going to be something like this, where you have an output and you just take a feedback, and then here it's just an add, and then you're adding one to this, okay, and this is your signal. Okay, so that's a counter in Faust, right? Cool. So if I were to say counter, I would just say something like tilde, underscore, and then underscore plus 1. Right? And then if I call counter here, that's my counter in Faust. Okay. And if I wanted to use partial application, I could put parentheses here, get rid of the plus. Okay, so this is the same as before. That's the partial application. Cool. How do I verify that this is a counter that counts one by one in Faust? In the Faust Web ID, there's this very convenient tool that allows you to plot the output of a Faust program. So if you click on plot first samples, you can see that it's drawing a straight line. Okay, those are samples, those are values of your samples. Again, so here we're drawing a ramp. So looks like it's working. If you click on oscilloscope here, you have different ways of visualizing the data that are coming out of the Faust program, and one of the ways is to get the samples. Okay, so you see that first sample is 1, second sample is 2, 3, 4, 5, 6, 7, 8, etc. Okay, so it means that my program is actually working. Okay, it is actually outputting what I want. Okay, so how do I turn that into an oscillator? Well, we're not even talking about sine waves for now. Let's say that we want to turn this into a sawtooth wave. How can I turn this into a sawtooth wave? Yes.
Mod 1.
Yes. Well, not one. Here we're counting one by one.
Oh, right.
Right. So mod whatever, you know, like, you know, okay, so I would say that after my counter, well, or actually I could keep it here for now, okay, I would connect this to a modulo operation and say that I'm doing a modulo of 100, and then if I plot the samples, again, you see that it's actually blinking like a sawtooth wave. Okay, so who never heard of a modulo operation before? Okay, so the modulo operation is something that we use a lot in computer science, and it gives you the remainder of integer division. Okay, So it means that if you do, say, 10 modulo of 100, the result of this operation is going to be 10. If you do like 50 modulo of 100, the result is going to be 50, okay? And then, if you do modulo of 101, then the result is going to be 1, okay? And then 102, the result is going to be 2. 202, the result is still going to be 2, okay? So this is very convenient to sort of reset the system that we have here so that it goes back to 0, okay? Cool, so now we have a sawtooth wave. Can I play this sawtooth wave the way it is right now? No, why? Yeah.
Because it has to be between -1 and 1.
Absolutely, okay. So how do I do this? I divide by 100, right? First. So now if I plot samples, now I'm between 0 and 1, okay, which is already better. And so after that, all I have to do is do, for example, so I could do this in a slightly smarter way, you know, but this is just like so that you see all the different steps, you know, and so I could say that I multiply this by 2 and I subtract 1, okay, and so now I'm between -1 and 1, okay. Cool, so if I run the program, it makes sound, that's a sawtooth wave, right? Oh, and that's the block diagram. So I have a counter, the counter adds 1 at every sample, then I do modulo so that whenever it goes above 100, it's resetted to 0. And then I do all these scaling operations so that whatever I have is a number between -1 and 1. Okay. So there are many things that I could improve in this algorithm, which is not very well written for now, but okay. First thing is, do you think that's a good place to put modulo? If I ask, the answer is probably no. Okay, why is it a bad place to put modulo?
Because if you leave it running long enough, will it just give some error if the number's too big?
Yeah. So, you know, computers are pretty dumb. They are not infinite. And so whatever variable you're using internally to store the value of this counter, eventually it's gonna be too big to actually fit in that variable, you know? So, you know, it's actually gonna happen very, very quickly, because integers on this computer in the web browser, they're stored on 32 bits. So, you know, it means that whenever you're gonna pass like 1 million or something like this, you know, like it's probably gonna wrap, okay? So, all that to say that this is a very bad location to put the modulo operation, and we probably wanna put it more in the loop, okay? Because if we put it in the loop, it's not gonna change anything except that we're gonna make sure that the loop doesn't ever exceeds 100, okay? So that's why I'm just gonna put it here. So I'm gonna put parentheses modulo 100. Cool. So it doesn't change anything again, you know, like except that we make sure that there is not going to be any numerical overflow at any point in the system. Although in that very specific case, it doesn't matter that much because we're working on integers. And so because we're working on integers, even if there's a numerical overflow at some point, which there will be, anyway, it's gonna wrap on an integer, and because it's gonna wrap on an integer, it's probably not gonna break anything, you know? So, still fairly safe, but it's definitely better to write things like this, okay? Cool, so now how do I turn this into a sine wave? Oops, sorry. Should be pretty straightforward. Like currently, this is what we have. How do I turn this into a sine wave? I mean, there are many ways to turn this into a sine wave, but there is one way which is easier than the others. And so here we're not really trying to make something which is too optimized or whatever you want. So, any thoughts, idea?
You just take the sign of the counter.
Yeah. So, I'm gonna remove this so that we're back between 0 and 1, okay? So this is 0 and 1. And so I'm just gonna connect this to a sine function, like mathematical sine function. So the output of this operation is now connected to the sine function. Is this gonna work? No. Why is it not gonna work? Well, we can plot and see what happens. Okay, so it's going in the right direction. You can see that this is kind of looking sine wave-ish, sort of, but it's not really a sine wave though. So how do I turn this into sine wave? Like, what am I missing? Okay, what is the main argument of the sine mathematical operation? There is only one argument to the sine mathematical operation that we're using here. Angle. Angle, great. In what unit?
Degrees or radians?
So usually degrees are like in like middle school or high school, you know, like that. No, but that's not what I in like usually in like in computer science and for like engineering, like you don't really use the sine function to do like angles like this, but you actually use radians. Okay, and that was not it's not what I meant. I still use degrees a lot. Don't worry. Okay, so we want to use radians here, okay? And so what is the range of, let's say you have a circle, what is the range in radians of that circle in radians, like the angle? So in degrees, you would go from 0 to, yeah? And so in radians, you would go from 0 to 2 pi, okay. Cool, so we want to make sure that this operation here goes from 0 to 2 pi. How do I do this? I multiply by 2 pi. 2. And pi is available in Faust in ma.pi. Okay, so now if I plot it, sine wave. Great, so if I run program, sounds like a sine wave. Cool. So the whole reason why I'm showing you all these things, is again so that you get a very basic understanding of how Faust works at a lower level than what we've done so far. Okay. So do you have any questions about this? Does that sort of make sense, or at least do you get like an intuitive understanding of that, or is it like completely obscure? Okay, I'll take that as a yes. For now. Again, like we're never gonna use things that are that low level in 258. This is just so that you have an idea of how this works. Okay. Cool. So there are two last things that I wanted to show you today with Faust. The next one is how you create a condition in Faust, because this is actually something that you're probably going to have to do in 258 at some point. You know, so and by condition I mean like how do you create, say, an if statement. So for example, say that I want to make a synthesizer and I want to have a user interface element that allows me to choose between a sine wave and a sawtooth wave. Okay, how do I do this? Okay, so first I'm gonna say that I have a sine wave. You know, I'm gonna give it a static frequency. You know, this is just for the sake of the example, and I'm gonna say that I'm adding the sine wave to a sawtooth wave. So I don't know if you remember what I said last week, but in Faust, you can't really create an if statement, because an if statement is a concept that only exists in imperative programming languages. Faust is not imperative, it's functional. So there is no such a thing as an if statement. Okay. Cool. So the next thing that I want to do is I want to create a user interface element which is going to allow me to choose between a sine wave oscillator or the sawtooth wave. So I'm going to call it cell for a selector, and I'm going to say that it's a numerical entry, and I'm going to call it selector in the interface, and I will say that the default is 0, the minimum is 0, the maximum is 1, and the step is 1. Okay, so here I'm creating a numerical entry, so it's just something where I can put a number, and this number can be either 0 or 1. It cannot be anything else. It cannot be anything else because the step is 1. So this thing can only do 0 or 1. Okay. So what I'm going to say is that 0 is for the sine wave, 1 is for the sawtooth wave. Okay. So now, how do I plug this to this? Well, for the sawtooth wave, it's pretty straightforward, because I'm just going to say that sawtooth is going to be multiplied by cell, okay? Because if cell is 0, I want the sine wave, so I want to kill the sawtooth wave, so I'm going to multiply the sawtooth wave by cell, so that when it's 0, it doesn't make any sound. Okay? Then I want to do the same thing for sine wave. And so for the sine wave, I'm going to say that, well, there are different ways of doing this, you know, like, but for this very specific example, I'm going to say that cell equals 0. Okay? So I'm doing a Boolean comparison here, and I'm using the result of this Boolean comparison to do a multiplication with whatever I want to kill, you know? Okay, so just to push the example slightly further, now say that I want to have a 3-ways selector that allows me to select between a sine wave, a sawtooth wave, and a triangle wave. Okay. So in that case, I do need to say that cell here is equal to 1, okay? And I'm gonna say that I have a triangle wave whose frequency is 440 hertz, and I'm multiplying this triangle wave by cell equals 2. Okay, and now I can say that the range of my numerical entry is 0 to 2. Does that make sense? Okay, so now if I run the program, I have a sine wave with 0, I have a sawtooth wave with 1, and I have a triangle wave with 2, okay? So I implemented a comparison. It's not using an if statement, it's using Boolean operators, okay? But it's fine, you know. Okay, so at this point, I'm pretty sure that some of you are like, yeah, but if you do this, it's probably not going to be very optimized, because you're computing sine and sawtooth and triangle probably all the time, you know, like even though you're multiplying them by 0. Well, the Faust compiler is smart enough to take care of that. So, so if you multiply a certain thing by 0, it actually automatically stops computing it. Okay, so so this is safe to write things like this. Like it's not going to have an impact on computation of the program that you're writing. Yeah. Yeah.
When you say it's safe, it's like, is it during compile or during run, like when it's running?
At runtime.
Oh.
Yeah. Okay, so that's for comparisons. Another thing that I wanted to show you that has nothing to do with this is how you create iterations. So how you duplicate something, basically. Okay. So say that you, for example, want to implement an additive synthesizer, which is going to be based on 3 sine wave oscillators in parallel. You can actually use the par operator to do this. Okay, so say you want to put 3 sine wave oscillators in parallel. One way to do this is to say, okay, I have my sine wave oscillator whose frequency is, okay, like 400, and I'm gonna put another one in parallel, and then another one in parallel, and this one has a frequency of 500, this one has a frequency of 600, and then I want to add them together. So to add them together, I could use the merge operator, and so I'm merging this into one signal. Okay, so now I have 3 sine wave oscillators in parallel, and they are being added towards just one signal. Okay. So what I wanted to show you here is how to automate this process here, you know, because there is actually no need for writing os.osc 3 times. You can actually do this automatically. So this is one way of doing this. The other way of doing this, I'm going to show you how to do it here. So I'm going to say that I'm using the par operator. The par operator allows me to duplicate things in parallel. It has 3 arguments. The first argument is going to be a variable. And this variable is basically, so you know, if you do a for loop, that's the I in the for loop here. Okay, so that's basically the variable that's going to store the current value of the iteration. Okay, so it means that the first time I is going to be equal to 0, the second time I is going to be equal to 1, and the third time I is going to be equal to 2. Okay, then I'm going to specify the number of iterations. So here 3. So okay, here I'm saying I'm going to duplicate something 3 times in parallel. Okay, and the third argument is the thing that I want to iterate on. So it's going to be os.osc. Okay, and so if I do this, now I have 3 sine wave oscillators in parallel with a static value of 400. Okay. So how do I do the little funny thing that I did above where I had 400, 500, 600? Well, I can use I to do this. So it means that, for example, here I could say that I have multiply by 100. Right. So now, the first iteration I is equal to 0, so 0 multiplied by 100, 0, and 400. So 400, 500, 600, right? Does that make sense? So now this is completely parametric, you know, like, so say that if I want to have 100 oscillators in parallel, I can have 100 oscillators in parallel, okay? Is the TNZ going to be able to compute that in real time? Maybe not. Actually, probably, you know, like the TNZ is actually very powerful. Like on the TNZ, you can probably run about 500 or 600 oscillators in parallel. So, so it's very beefy from a computational standpoint. It's not very beefy from a memory standpoint, and we'll see later during the class that it's going to be a big problem for you guys. And so it's like, oh yeah, I'm going to run this and I'm going to run that, you know, and then eventually you're like, oh, it doesn't work, I don't know why, you know, and usually that's because the TNZ doesn't have enough memory. So. Cool. Okay, so one very last thing that I want to show you very, very briefly, because it's almost the end, but everything you do in Faust, and that's kind of the main power of Faust, everything that you do in Faust here in the web browser, you can actually export it to most platforms that exist out there. And to do this, you can do it directly in the web browser by clicking on the little truck here, and then you can choose a platform. And so say, for example, you want to turn this into an Android app. Just click on Android, you choose architecture on Android, and then you click on compile. Then you wait probably for 3 minutes because it takes a while to compile an Android app. And then you're going to get a QR code, and you just scan the QR code with your phone, and you can install the Android app on your phone. So this works for Android, this works for pretty much everything that's available here. You know? So if you want to make like audio plugins, like VSTs, audio units, if you want to make like a plugin for Unity, for example, you can do that. If you want to program the TNZ, you can program the TNZ. If you want to program the ESP32, you can program the ESP32. So all that to say that the main strength of Faust is this, you know, it's its ability to go from the web browser, which you use as a prototyping platform, to pretty much any platform and standards that exist for audio processing. Yeah, I know that some of you made a weird face when I talked about the Android app, but so because you're probably like, okay, what is the corresponding Android app to this? You know, since the current program doesn't have a user interface, it's just going to be an Android app that when you open it, it doesn't have a user interface, and it's 100 sine wave oscillators added together, making a weird sound. You know, like that's your Android app. Okay, but if you add user interface elements like the numerical entry that we have here, or like sliders, buttons, or whatever, they will show up in on the screen of your Android phone. And you can even like use accelerometers if you want to. You can do like accelerometers mappings directly in Faust if you want to use the built-in accelerometer of your phone. This is crazy. It didn't used to do that before. Like, I'm not sure why.